And what we have already done is we have calculated the correction due to the relativistic motion of electron, because uh, the electron is revolving around the nucleus, and it's revolving with the speed that's close to the speed of light. Now we have to go for the analysis of another correction, and that's the correction due to the spin orbit interaction. And what spin orbit interaction means is that if I assume that an electron is revolving around the nucleus, this electron has orbital motion, and this orbital motion is equivalent to a current loop, and therefore automatically there is magnetic field linked with this orbiting electron. So you will have the magnetic field due to the orbital motion of this electron, and at the same time this electron has its own spin angular momentum. So you have, say, the magnetic field due to the orbital motion, and at the same time you have the magnetic field due to the spin motion of electron. And so there is a spin orbit interaction involved here, and this spin orbit interaction will certainly have an influence on the overall energy of this atom, or overall energy of this system. And to analyze this spin orbit interaction, if we think about the magnetic moment, and try to achieve the relation for orbital magnetic moment of electron. So for that, what I'll have is that this electron is revolving, and this orbiting electron traverses this circular orbit of radius, say, r, in the time t. I mean, t is the time period of this electron, so that the time it takes to come back to some assumed position. So I can this revolving electron, this orbiting electron, is equivalent to the current, and the current that measures is simply the rate of flow of charge. Now here I have one electron, so I'll take E, and the time to complete one revolution is capital T. Now this electron has the uniform it has a uniform speed, and that speed is the distance that it travels in an orbit. That will be 2 pi r by t. So this implies that this t is 2 pi r by v. And I can use this value of t in this equation, and I can get current. This current is it is e by 2 pi r, and this v will go up. So what I'll have is current is e v by 2 pi r. Now, from the definition of magnetic moment, how do we define magnetic moment? We define it in terms of the product of current and area. So this is my mu L, and this mu L is current into area. So current we have calculated, that is EV by 2 pi r times the area of this loop is pi r square. So what we'll get here is E, this pi and r and square will cancel, so we'll get EVR by 2. And we can write here this mu L is it is EMVR by 2m. You can write it this way. So this mu L is E by 2m. This mvr is nothing but the orbital angular momentum. So I'll be using here L. So if I write down this equation in vector form, this will be mu L is it's minus E by 2m L vector. And what's evident from this equation is that this orbital magnetic moment of the electron is in opposite direction to the angular momentum of this electron. So at the same time, we can similarly write down the magnetic moment for the spin using same analysis. So what will be that? That will be mu s is minus E by 2m s. And this s refers to the spin angular momentum of the electron. But for electron, what we have two directions for electron, two directions in terms of its spin. So this mu s can be written minus 2 times e by 2m s vector. This 2 and 2 will cancel, so the spin magnetic moment of the electron is minus e by m s vector. Right. Now, so what we have here, we have a situation where there is an interaction between the spin magnetic moment of electron and the orbital magnetic moment of electron. And for the sake of argument, I mean, if the two magnetic momenta, or if I talk about this situation in terms of the magnetic field, if the magnetic fields are aligned in the same direction, in this case, what we will have, we will have decrease in energy, and at the same time, if the magnetic interactions are in opposite direction, this will lead to repulsion, and there will automatically we will have the increase in energy of the system. Now, if I take a trivial way of, so what I have is, suppose this is mu L. I mean, we have the magnetic field due to the orbital motion of this electron, and we have mu S, and this is magnetic moment due to the spin motion of this electron. Now, if this is the case, so there has to have the magnetic field. That's why I'm showing the lines of this magnetic field. So what we have here is that if I assume that there is an angle of theta between this magnetic field that leads to mu L, and mu S is the magnetic moment, spin magnetic moment of this electron. So what we will have here is we will have the storage, if this because this mu S can act as a dipole, and this mu S can move on, and there can be storage of energy. And how can we write down that energy? We can write down that energy as, if I assume that energy is U, that potential energy is U, that will be minus mu S dot B. Right. Now, what I want from here is, I want to calculate this magnetic field in terms of the electric field of the nucleus. Now, so what we have electron, and this electron is orbiting, and it will have its magnetic field. If I have to write the magnetic field, I can write it 1 by c square E cross V. Obviously, the problem that we have been discussing here, there certainly is involvement of the electric field, because the charges are involved in this problem. So we have electric field, and if I had to write down the electric field of the nucleus, that electric field is going to be 1 by 4 pi epsilon naught ZE by R square. Now, this Z is the number of protons that are there in the nucleus, and R is the radius of the orbit. Now, if I write down this equation in vector form, for here I have vectors. If I write down this equation in vector form, I can write down this En vector is 1 by 4 pi epsilon naught ZE by R cube R vector. So I can use this. I'll call it 1 for the time being. I'll call this 2. I'll call this 3. I can use this this expression of electric field in equation number 2. What I'll get, I'll be getting this magnetic field will be 1 by c square times 1 by 4 pi epsilon naught ZE by R cube, and then R vector cross V vector. Yeah, that should be the case. Now, I can write down this magnetic field as 1 by 4 pi epsilon naught c square and r cube. And here I'll have m r cross v. So I can write down here m. So I have multiplied and divided by m. So this m r cross v is it gives me the measure of the orbital angular momentum. So this b, the magnetic field, is 1 by 4 pi epsilon naught c square r cube m l vector. That's the case. Now I can use this value of magnetic field in this potential energy. So I can use the expression of magnetic field here in this equation. And what will I get? I'll get this U is minus mu. What I'll get here is minus mu s. But what is mu s? Mu s is it is what's mu s? It is minus e by m s vector. So here I will have minus e by m s vector, and then I have dot, and for after dot I have what I have is I have the magnetic field, and that is 1 by c square z e by r cube, or vector cross. Okay, I'm writing it wrong. So what I have is so let me write this again. So this u will be minus times minus e by m s vector dot 1 by 4 pi epsilon naught c square r cube m l vector. All right, so I can write down this u as so this u will be this u is going to be now so this minus and minus will give me plus, and what will I get? So I'll have plus here, and and what I'll get is ze square by 4 pi epsilon naught m c square m m square m c square c square. Then we will have m square here, because this m and m will multiply, so we are going to get m square here. So m square c square r cube and l vector dot s vector. Now what we want from here is that we want to have the operators of l dot s, and we want the the operator of r. We want the operator of r. So we want to evaluate we want to evaluate this l dot s vector in terms of operators, and acquire the final solution for it. So so to move on from here, if I take on this whole thing, this is u is say a times l dot s, for the sake of simplicity here. Now I want to calculate the Hamiltonian for this state is what? That is HSO. But this Hamiltonian, it will comprise the quantum mechanical operators in terms of Ls and in terms of R. So we have to evaluate these results to obtain the final equation. Now what this this L dot S comes out to be is it's A by 2 times J square minus L square minus S square. Now let's see first how does this result come out, because then we will be then we'll be looking for the expectation value of J square, L square, and S square. Now if I talk about the total angular momentum J, that is L plus S, and if I go with scaring this, what I'll get is J square is it is L square plus S square plus twice L dot S. So from here we will have L dot S will be J square minus L square minus S square by 2. So from here we have obtained this L dot S. So on evaluating the expectation value of J square and L square and S square, what we obtain is say now if I want the expectation value of this J square, what will be that? That will be psi NL ML J square psi NL ML. So after evaluating this, what we have done already in the foundation quantum mechanical course is from here we will get the value will come out to be J times J plus 1 h cross square, where this J is the total angular momentum quantum number. This J is total angular momentum quantum number. And similarly, for L square, we will have the same kind of mathematical quantum mechanical treatment for L square and psi and L M L. And from here, what we obtain is L times L plus 1 h cross square, where this L is orbital quantum number. And finally, for S square, for S square, the expectation value of S square, what we will have is psi n L M L S square psi n L M L. And what the result comes out is S times S plus 1 h cross square. So now we can use these results in the correction of spin-orbit interaction. See, here we have only taken into account the dot product of L and S, and so this HSO, I should call it HSO1. Okay, this HSO1 is it's going to give me the energy, and because we have evaluated these values are evaluated, so we will have ESO1, and that is A by 2 times J into J plus 1 minus L into L plus 1 minus S into S plus 1 h cross square. And then we have another term that I talked about is the expectation value of 1 by r cube. And this expectation value, psi NL ML, 1 by r cube, psi NL ML, this expectation value, it comes out to be z cube by n cube L times L plus 1 times L plus 1 by 2. So what we have is HSO1 and we have ESO1. So here I'll call it HSO2. So when we have calculated its expectation value, so this is ESO2. So we have an overall correction to the Hamiltonian in terms of spin orbit interaction of electrons. And to write down the final expression for this correction, so we can write down this HSO as R alpha square z to the power of 4 h c by 2n cube L times L plus 1 by 2 times L plus 1, and then we have J times J plus 1 minus L times L plus 1 minus S times S plus 1 divide by nothing. Okay, so we can boil down this whole thing to some other constant. So this HSO is say I'll call it A1, h cross square by 2 times j plus 1 minus l plus 1 minus s plus 1. So what do we conclude from the results that we have, the crazy results that we have obtained here, is that this HSO, the correction to the spin orbit interaction, what it does, it depends on the fourth power of the charge of the nucleus. And at the same time, what we see here is that the spin orbit interaction is dependent on the total angular momentum quantum number J. Now, if we try to analyze the results that we have obtained here. Now, if I take the state n is equal to 2, for n is equal to 2, what I have is I have I'll have L is equal to I'll have L is equal to 1, and I'll have L is equal to 0. For L is equal to 1, I will have the P. For L is equal to 0, I will have S. All right. Now let's go with the J. Now what is J? J can be L plus minus S. So J can be it can be 3 by 2, and if we add the 2, and it can be 1 by 2. So what it means now is that there is splitting. There is splitting of lines. And how can we analyze this now? Now if I choose this is my P level, and this is my S level. In the P level, what I have is I have 3 by 2, and I have 1 by 2. This is J, and this is J. And for P, what is L? L is equal to 1. And for S, what is L? L is equal to 0. And for S, I simply have J as 1 by 2. So I would like to generalize what we have done till now is we have a situation where we have, suppose we have a level, and then this level has two states, and one state is P state and another state is S state, and these two states are a result of correction in relativistic motion of electrons kinetic energy. So we have a correction, and that correction gives birth to P and S for this n is equal to 2 state, and it gives birth to P and S. Then when we talk about the spin orbit interaction, what happens here is that we have splitting. We have 3 by 2 for J, and we have 1 by 2 for J, and we have 1 by 2 for J for S state. So this splitting is the result of spin orbit interaction. So this result can be assigned to the spin orbit interaction that we have. Now let us try to do the same analysis for n is equal to 3 state. Now if I have n is equal to 3. So taking n is equal to 3, what I have is here I will have L will have 0, 1, and 2 states. Okay, so L cannot be more. L has to be less than n, and so what we will have a state here, and we will have another state here, and we'll have. Okay, I should take it separately. I should have taken it separately. Okay, let me take another state, and let me take another state. All right. Now this is my L is equal to 2 state, this is my L is equal to 1 state, and this is my L is equal to 0 state. Now what is happening here is we can calculate, and we can see that it will split down into the two parts. So that is here J will be 5 by 2, and here J will be 3 by 2. And again here we will have two splittings. Now for L is equal to 2, we have the D state here. For L is equal to 1, we have the P state here. So this is going to boil down into two states. So here J will be 3 by 2, and here J will be 1 by 2. And here for L is equal to 0, this is the S state, we will have J equal to 1 by 2 state. So what we see here is, till now we have incorporated the spin orbit interaction to the original Hamiltonian, and we are in a position to see that n is equal to 3 level has actually 5 levels in it. But in actuality, what we find is in the original experiment, when the experiment is performed, for n is equal to 3, we have 7 levels. Now, the next correction that's to be added to the original Hamiltonian, that comes in terms of what's called as Darwin correction. Now, this Darwin correction is basically, the basic idea of this Darwin correction is that the electron that is in the S state, its speed is more than that of the electron that is in the P state. So the idea is quite numerical, in sense that there has to have a correction that's to be added to the original Hamiltonian for this atom, and that correction can be attributed for the state S, because in the state S the electron is revolving with the speed greater than that of the speed of the electron that's having motion in the P state. And what this Darwin correction is, its value is it's positive, so it has to be added, and it comes out to be equal to Z alpha by n cube whole raised power 4 RHC. Now this correction is valid only for L is equal to 0 state, and this correction is not to be introduced. This E is 0 for L not equal to 0. So this Darwin correction has to be attributed only for the state L is equal to 0, and for all other states its value is equal to 0. Now, if I take on if I take on this n is equal to 2 state again, so n is equal to 2, what we have P and we have S. So this is P and this is S, and this P splits for n is equal to 2 state. For this J is 3 by 2, and for this the J is 1 by 2, and for S J is simply 1 by 2. Okay, and taking into account the Darwin correction is that this state, since the speed of the electron in this state is more, so this state has to be the part of this state, what is called as what's J half, the substate of the p orbital. So what would it look like is that for n is equal to 2, for the sake of understanding here, this is my p state, and it has a doublet, and it has the S state. This S state will not exist here. This S state will be the part of this state. So what we will have is J 3 by 2, and here we will have J 1 by 2 and J 1 by 2. Now, writing down in terms of the orbitals, so here what I will have is I will have 2p 1 by 2 state and 2s 1 by 2 state. They'll be on the same level, and this J 3 by 2. So here we'll have J 3 by 2. The two states, will be enclosed by the same level due to the Darwin's correction. So to summarize the things that we have tried till now, is what we have is we have the the overall Hamiltonian, and we have added the terms due to the perturbations that are involved in this problem. So that is H0 plus H or CK plus HSO plus H Darwin. So for every Hamiltonian, we have the corresponding eigenvalues. So what we will have here is this is En and plus ER plus ESO plus ET. So I will write down this as En plus E dash. So E dash will take care of the terms that have been added to the original Hamiltonian. So when all of these terms are added mathematically, when all the modifications that are done, we achieve the final equation for this E dash. And what is that? What is that E dash? This E dash is what it comes out is R NC by it's H or HC by N cube Z alpha whole square times 1 by J plus half minus 3 by 4N. And what we see here in all this equation, what we see here is that the corrections that we have calculated, these corrections are purely dependent on J. And what is J? J is the total angular momentum quantum number, and depends on N. And what is N? Is the principal quantum number.